Hi everybody, I'm the greatest living inventor, and today we are doing my invention, mass driver repeater. So I'll write it down. Mass driver repeater. Okay, and another title for this is repeating electromagnetic launcher. Repeating electromagnetic launcher. Okay, so I'm not starting to explain as I usually do every word, like what is mass driver. You should read about it in Wikipedia. It's basically a way to launch something like a load with the electromagnetic gun into space. But if you want, I'll give you links and you can look it up, everything in Wikipedia, because it's a long invention and we need to hasten things. Okay. An efficient system. Sorry, I'll take off my shirt. Okay. An efficient system to send packages, not people, between planets by connecting the idea of a repeater from telecommunications to the idea of a mass driver from non-rocket space launch or spacecraft propulsion. Mass driver repeater. Need one. Okay, the first thing that we need, the requirement. On Earth and on Venus, we have too much CO2. On Mars, we have too little CO2. We need to transfer some CO2 from Earth and Venus to Mars. On Mars, this will thicken Mars's atmosphere and help start greenhouse effect to warm it. On Earth and Venus, this will do the opposite, stop the greenhouse effect. This way we make all three planets habitable. This is like the ultimate free meal. Keep your planet and get 2 more for free. By the way, after thinking about this independently, I found out that people have already thought about some of this before. See discussions in Quora and in Reddit. Moving CO2 to Mars. If it was possible to collect half of the atmosphere of Venus and deposit it on Mars, would this make both planets more habitable? Okay, someone already asked this. So my original contribution here will be only the how-to part. Okay, need 2, requirement 2, something else that we need. The first humans on Mars will need large amounts of oxygen, water, food and fuel. We need to transfer these from Earth. How do we supply both of these crucial needs? What we want is a huge pipe or conveyor belt that takes a payload, cargo, from planet to planet. But since the cargo can fly freely most of the way, it will be made of a few separate stations. The stations will of course be floating in space. The ones next to a planet can float in a Lagrangian point so that it follows the planet but doesn't fall onto it. The engine that makes the payload fly from one station to the next is a big coil gun energized by solar power. Okay, so the engine, I'm counting on you that you will see what a coil gun is from the short videos. Here is a very nice video, GreatScott by GreatScott. He's a German guy, about what coil gun is and how you can build it yourselves. So I'll put it in the links or in the description. Make your own coil gun by GreatScott. Okay, and in the context of space, it's called a mass driver. And that's not a new idea either. A video from Space Studies Institute, which was founded by Gerard K. O'Neill, who built the first proof of concept. So I'm putting this one also in the description. The video is called SSY Do-It-Yourself Mass Driver Demonstrator, and it's from SSI Space Studies Institute. So another video. And it's by SSI. Space Studies Institute. Okay. So you should watch these two, and I'll put it in the description of the video. Okay, so what's new? Up until now, mass drivers had only two flavors. One, anchored on solid ground, Earth or Moon, and shooting payload into space. 1.1, okay, one subsection, first subsection, shooting a spaceship to the moon, like in 0 to 80 by Edwin Fitch Northrop from 1937. Okay, it's a book called 0 to 80. I'm not expecting you to read it. I didn't read it either. It's just that the idea comes. The first mention of the idea is there. So 0 to 80. And It's by Edwin Fitch Northrop from 1937, or to Earth orbit. Okay, so again, I'm reading the whole section. Shooting a spaceship to the moon, like in this book, or to Earth orbit, like in another book. The moon is a harsh mistress. The moon is a harsh mistress, by Robert A. Heinlein from 1966. Okay, so the moon is a harsh mistress. Okay, it's also with the mass driver from 1966. Okay, next subsection 1.2, shooting construction material from the moon to a colony in space, like in NASA's Space Settlements, a design study from 1975. Okay, I'm not writing everything, I will put it in the links. Okay, if it's important, I will put it in the links. 1.3, shooting on a spaceship that reflects like a solar sail. Reflects in quote unquote. Reflects the bombardment to propel a spaceship away from it, or to shoot supply of fuel. Okay, so that's another option, like shooting supply of fuel, or shooting and it reflects like a solar sail. 1.4, another example, shooting around the circular track of a space fountain to hold up a tall structure. Okay, space fountain is a very cool thing, but I don't have time to go into it. It's made by Robert L. Forward. Okay, space fountain. Okay, I'll skip it because I'll need the time later. What time is it now? 13 minutes. Okay. I'll just write the name. Space fountain. It's not our issue now, but it's so cool that I want you to know about it. Robert L. Forward. Okay, who was a physicist and a sci-fi author. Okay, okay, so this is one kind of mass driver, one flavor of mass driver that we had up until now, and the second type is of flavor is floating in space on a spaceship, and used to propulsion engine as propulsion engine to move the spaceship, like ion drive. Okay, so another thing, ion drive. Okay, so all these are those that we talked about are stationary and shooting things into space, and this one is moving. Okay, this one moves the spaceship. Okay, so my idea is to combine these two types together, floating in space plus shooting payload into space. There are two possible routes. Route 1, a straight line. Okay, so I'm erasing and starting to write. Straight line. This can use end stations. Okay, end stations without middle stations, and both ends in the middle. So this can use only end stations without middle stations. Can accommodate high frequency transports with large volume. Initial huge CO2 transport. Only available over the short period of time when the two planets are close. When the two planets are close by, let's say when Venus is closest to Mars, because we want to move a lot of CO2. The straight line stations will basically be a piece of hollow pipe with both its edges open, floating in space. Okay, so it's basically a pipe. Okay, I'm not writing because again we will need the time later. It's very long. But just so that you have in mind, it's an open pipe. Okay, here is space, here is space, the whole thing floats in space, and it's like a hollow pipe. Okay. Indirect curve, okay, another possible route, indirect curve. Must use this one, must use both end stations and both end stations and repeater stations in the middle. Can only handle low frequency transports with small volumes. Routine supply supports like the oxygen and fuel and things we need to move after we terraform Mars, and we want the people to, well, not completely terraform, but like the necessary fuel, oxygen, water, things that we need all the time in small quantities. Not like the huge quantity of like the CO2. We are still here. Available all year around, even when this destination planet is behind the sun. Okay, if you look at it from above, okay, if we have the sun, okay, this is the sun, and let's say this is the Earth. And this is the blue planet, and this is Mars, the red planet. So, but if we want an indirect curve, if we want to pass around the sun, so we need the indirect curve. Okay, so this is available all year round, even when the destination planet is behind the sun. The indirect curve, middle stations, will basically be a scoop wheel rotating in space. Okay, scoop wheel is a wheel that is used like a pump to take water from one place to a higher place, and you can look it up in Wikipedia. So it will be like the middle stations, if there is one station here and one station here and the middle station here, so the middle station would be like a scoop wheel. Rotating in space. Okay, I'm choosing a shape of a disk and not a sphere, okay, for the scoop wheel. A disk and not a sphere, because all the planets in our solar system rotate around the sun in the same plane. Okay, if you put here, if you look from above, or I'm sorry, if you look from the side, they are all on the same plane. Okay, if you put here Venus and all the planets, they are rotating in the same discus. And rotate around the sun in the same plane, so we never need any flips at all. Flips, I mean when we change direction. Okay, so we don't need it. The scoop will be a clamshell bucket. Okay, clamshell is when you have on a crane, if you have a lifting hook, and it's like something that looks like this. Okay, it has a hinge here and here and here, and it's like I'm sure you've seen it hundreds of times. It takes something and closes like this. Okay, so it's like a big crane that has the bucket or the scoop made like this, that it closes and lifts. So this is called clamshell bucket. Okay, which can catch and release the payload or the counterweight. I'll talk about what the counterweight is. This scoop can be connected to some rope or chain and be shot to catch its target and then be retrieved. Since the release needs to be more accurate than the catch, I think we should open the clamshell bucket after the catch and rely on the electromagnet to hold and release. Because the system has to take a lot of beating from catching the payload and counterweights, it has to be tough. Something like bucket wheel excavator. Okay? Again, you can look it up in Wikipedia. Bucket wheel excavator. Okay, I'm sorry we are in such a rush. We need to do a lot of drawing in the actual explanation. I try to save energy as much as possible by compensating, which means offsetting or deducting, one movement with a movement in the opposite direction. Nevertheless, all the stations and especially the middle ones, okay, like here, must move themselves in space to align towards the other planet, and the middle ones in the straight line case needs to flip. Okay, so in the case of the middle ones, you will see it when I'll explain it. Okay, so if you need to, you can go back in the video. So also another thing that requires energy is that needs to move itself is the straight line case, the middle stations, not the middle. In the straight line case, they need to flip. So flip over, okay, like rotate 180 degrees. So this will be done by having each of the payloads carry with it a part of its main load, also some amount of frozen CO2. When docked or parked inside a station, the station will connect with the hose and sublime some of this CO2. In parentheses, dry ice turns right into gas, so no messy liquid, close parentheses. With the gas compressed in the station can release the gas from the right nozzle into space to move the station in the desired direction. Okay, so if we have a station and it took inside a package, cargo, and on the cargo there is a small tank with the tax of tax. It's a metaphor for of the CO2. I'm sorry, the CO2. So now the station has takes this CO2 and through a pipe. It doesn't take the tank, it takes the actual CO2 and store it, and then if it needs to flip, it can put it out of this nozzle, for example. Here there is a nozzle and it can flip. Okay, so okay. With the gas compressed in the station can release the gas from the right nozzle into space to move the station in the desired direction. And it has all sorts of nozzles which it can help it to move or rotate, flip. You can imagine this extra payload of CO2 like a tax. Okay, so the CO2 is a tax. Tax that each has to pay in order to pass in the station. I'm sorry. The middle stations take more tax because they need to maneuver more. Before each pass, before each pass, the throwing station aligns with the catching station using lasers and clock and trigonometry. Okay, now a big issue, recoil problem in the straight line. So now we are talking about the recoil. Problem in the straight line case. When we shoot any gun, the gun is pushing the bullet forward and the bullet is pushing the gun backward. This is Newton's third law, action and reaction. How can we prevent our mass driver from being pushed backwards into space? I got this idea from the Funicular railway, which operates underground in my hometown, Haifa, which is called the Carmelit. Okay, it's funicular, it's like, it has a wheel and a chain, and here is one, it's like a street car, but like cable car, but around, they are both hanging around the same wheel. So this goes down when this goes up, and this, they balance each other. Okay, so, and it's called the funicular. This is the general term, and in Haifa it's called the Carmelit. So I got it, the idea, I got it from there. So in the Carmelit, the two cars are tied to both sides of a rope that is hanging on a pulley. Each car's weight balances the other car. My idea is that every station here will simultaneously shoot both forward, the real payload, and backward, a counterweight with the same mass. Let's think of an example system with 5 stations along a direct line. We'll call them A, B, C, D, E. The end stations A and E are anchored to planets. Okay, so let's draw this. I'll erase everything. Okay, so so our stations are A, B, C, D, and E, like they are in order, A, B, C, D, and E, and the end stations A and E are anchored to planets, like this is Earth and this is Mars. We will call the direction from A to E forward, and the direction from E to A backward. Okay, let me write it. Like if there is A, okay, so I'm drawing it in a very particular way, and you will understand why in a minute. Okay, again, Earth looks a little smaller than Mars, and it's actually the other way around, so let's make Earth bigger. Okay, so this is the blue planet Earth. this is what I call A. Okay, and B, C, D, E. Okay, so the last station is the red planet Mars. The middle stations don't have planets, they are floating in space. This is green, and this is orange. Okay, and this is supposed to be yellow, and I don't have yellow, so I'll make it out of orange and light green. I know it doesn't mix, but let's pretend this is yellow. Okay, it's not a special, it's a special station, but not, it doesn't supposed to have a special color. It's just that I don't have the right color, I don't have yellow. So let's pretend this is yellow. Because all the explanation that I wrote was in a book when I had yellow, so, and here I don't have it, and I'm too lazy to change the entire explanation. Sorry. Okay, so we will call the direction from A to E forward. Okay, so this is when we move like this, it is forward. Okay, if I'm saying we move from C to D, then it's forward. If we move from A to B, it's forward. And if we move in the other direction from E to A, it's backward. Okay, so you understand our system. If you can see the colorful icons, here you can. I hope you can see the colors. Yes, you can. So this is red, and this is blue, green, yellow, orange. I'm saying again the colors because I will use them a lot in the explanation. So this is blue, this is green, this is yellow, this is orange, and this is red. Okay. So if you can see the colorful icons, we are moving a full package from the blue planet on Earth. So we have a full package here. Okay, I will draw the full package like it's full, like this. So this is the full package. We are moving it from Earth to Mars. It's full of food or oxygen or water or fuel. And we are moving a full package from the blue planet on the left to the red planet on the right. And at the same time, we are moving an empty package from the red planet on the right to the blue planet on the left. Okay, so this is an empty package. And it's moving at the same time from the red planet on the right to the left, to the blue planet on the left. Each colorful icon shows what happens to his station, not to the package. Okay, so if we see this square, which looks like stop, you know, it's like you have on your CD or something these icons that this is play, and this is stop. I'm sure you know this, but just in case. Stop. And this is forward. And this is backward. Okay, so I'm sure you know this. So I will use this icon. So this is stop. This is now means that the station, not the package, the station is stopped. Also this station is now stopped. So it floats in space and is doesn't move. The station itself, not the package. We don't care now about the packages. We care about the station. This station is in place. It's stopped because it has this icon. Stop. Okay, I'm sorry about the noise from outside. I hope it doesn't get into here. I can't control it. Sorry. Okay, so initial condition before we begin is this. What you see here. I will erase the explanations. Okay, so okay, 42 minutes. I'll do it really in a hurry. I hope you can follow. At first, everybody is stable. We have a payload in A and the counterweight in E. This is the payload in A, and this is the counterweight in E. Counterweight. Payload. Okay, so what I'll do, I'll use the same drawing all the time to save me time, and you can go back in the video if you need to understand that this is the payload and this is the counterweight, the empty one. You see it's small, it's thin. It's empty, it's the counterweight, and this is full, it's fat, so it's the payload. Okay, so step one, this is the beginning, this is the initial stage. So step one, A shoots the payload forward to B. A is pushed backwards, but A is stable because it's anchored to a planet. This is on a planet, on Earth. E shoots the counterweight backwards to D. E is pushed forward. Okay, it's pushed to here. But E is stable because it's anchored to a planet, to Mars. This is Mars. So B catches the payload and B is pushed forward, and D catches the counterweight and D is pushed backwards. Okay, so our next stage is like this. Okay, this shows that this station is pushed backward, and this shows that this station is pushed forward, and this shows that this one pushed but it doesn't move. This one is pushed but it doesn't move because they are planets. They are on a planet. Okay, step 2. To balance this, B shoots and now this goes to here. Okay, so this is now attached to B from this side, and this is now attached to D from this side. To balance this, B shoots the payload forward towards C. So now B is stable. Okay, if this one is going to here, but it throws something forward, then it moves backward, so it's balanced. Okay, so this is now balanced. And B is now stable. At the same time, D shoots the counterweight backwards towards C. So now D is stable. So the package goes to here. The counterweight, I'm sorry, this is the counterweight, and this is now stable. So D is now stable. C gets them both at the same time from opposite directions, so C is stable. Okay, this is like a pause. It's stable. Okay, step 3. Now C needs to flip the payload and the counterweight. I think the easiest way is for C as a whole to flip around 180 degrees, like I've shown you before. So step 3 is just this goes to here and this goes to here, because this whole thing flips. Step 4, C is the middle station. It shoots in both directions payload forward to D and counterweight backwards to B. So C is stable. So the next step is that this goes to here and this goes to here. Okay, they are in the next station. And this is stable because it happens in the same time. Now D catches the payload from C. D is pushed forward. And B catches the counterweight from C. B is pushed backwards. Step 6. To balance B, B is shooting a counterweight backward to A. B is now stable. Okay, so it shoots it to here. This goes from here to here. And this is now stable. To balance D, D is shooting the payload forwards to E. Okay, this goes to here. So this is now stable. Okay, step 7. Now E gets the payload from D. E is Mars. E is anchored to one planet. And A gets the counterweight from B. A gets the counterweight from B. A is anchored to another planet, to Earth. In this example, we can do the same with like Venus and Mars, or any planet, any two planets. Okay, so I'm just finishing. This goes to here. And this now is stopped, and this goes to neutral. And I'm sorry, this was before was square. Okay, I skipped one. I forgot to change the end ones. The end ones, after they launch their package, either if it's a counterweight or a cargo, it becomes a stop. Okay, so this now goes to here. Okay, the cargo reached Mars, and this becomes neutral. Okay, so in the final stage, summary, after we finish, so now everybody is stable, and we we move the payload from A. Okay, so after he gets the package, it doesn't move, so we show it like a stop. And after this one gets the package, it doesn't move, so we show it like a stop. And summary, after we finish, so now everybody is stable. And we move the payload from A to E, and we moved a counterweight from E to A. Okay, recoil problem, this all was in the straight line. Now in the indirect curve. Recoil problem in the indirect curve. Okay, so now I'm really stressed on time, so I'll do it really in a short way. Recoil problem, indirect curve. Okay, remember when we have a Sun and Earth and Mars, for example. This is similar to the conservation of momentum in the straight line case, but here we solve it with angular momentum, like a flywheel energy storage. If you don't know what a flywheel is, flywheel. Okay, so if you don't know what a flywheel is, you can watch this short video by NASA 360. NASA 360. Flywheel energy storage. It's like a potter's wheel, they say in the movie, in the video. I'll put the link in the description. In the straight line case, we can, what we've seen up until now, we can get back to the original location of the station almost solely by the energy of opposing movements of the payload and the counterweight. Unfortunately, in the indirect curve case, both movements have a component away from the Sun which we can't compensate for. Okay, so I'll just draw it quickly. We have the Sun. Okay, this is the Sun. And we have, let's say, the blue planet and the red planet. And we have our potter's wheel, the wheel that we talked about, the disk. Okay, so this it's a disk. It's not a ring. It's a disk. But I'm trying to show that it's round, like I'm drawing it like a ring, but it's actually a disk. Okay, this is a disk. So and it rotates. Okay. So, unfortunately, in the indirect curve case, we have both movements both movements have a component away from the sun which we cannot compensate for. You will see in a minute. It's basically this one pushes it towards here and towards here, and this one pushes it towards here and towards here, so they are both pushing it towards here. So this is our problem, which we cannot compensate for. But if we let the station drift a bit towards the sun, then that's solved. The rest of the time we need to do corrections with CO2 as explained before. If the catch and release will be close in time, when this one and this one are close in time, the station scoop wheel doesn't move sideways very much. If there is a chance that the rotating station will receive both payload and counterweight at the same time, we need two scoops. The scoop is the thing that catches, like the bucket, that can move along the rim of the disk. So let's draw this step by step like before. So okay, so imagine that this has a scoop here, like the scoop is something that catches, and also it has a scoop here that catches, and it can shoot it on a rope or something. It can shoot a rope with that catches, and it can shoot a rope, another rope that catches. Okay, so I'm erasing this because it interrupts with the schematic. Okay, so let's draw this step by step like before. Step 0. This is before we start. You can see blue Earth on the left, and our gray payload is on Earth. Red Mars is on the right. As you will see soon, there is no need for the counterweight at all. Yellow Sun is in the middle, and the station is the light brown Tinker Toy wheel. I'll use another icon there above, which is rotating at the same direction all the time. Step 1. The station catches the payload, and the station is pushed upward and to the right. Okay, so this goes from here to here. And the station is going upwards and to the right. I don't have time for the fancy graphics. Step 2. The station throws the payload towards Mars. So the station is pushed upward and to the left. Okay, if this one throws the payload, after a while throws the payload, so it's pushed upwards and to the left. So remember these arrows, and now we have the station throwing this towards Mars, so it's pushed, the station is pushed upwards, this rotating wheel is pushed I'm sorry, to the left and upwards. Okay. Step 3, the payload is on Mars. Hooray! Let's put it on Mars. The right and left arrows from step 1 and step 2 cancel each other. So it looks like the up arrow remains. So we have this problem, but we talked about it that we just need to move a little towards the sun. So the up arrow remains. Step 4, not so, because the sun is attracting the station down all the time, which, if we position the station accordingly, cancels the up. Okay, so the sun moves here, so there is no problem. Okay, so I think that's it. Yeah. So there is another arrow, and it cancels out. Okay, so that was my invention, and I'll see you in my next invention. Thank you very much. Goodbye.